This is P.U.L.S.E, Platform for Understanding Load Shaping in Events. Scratch that. It's a crash test.
My name is Chaz, and I'm going to be walking you through the process our team went through to produce an effective P.U.L.S.E system. Our customer request was simple: design a system to simulate and measure a crash event, capturing motion data being acceleration, velocity, displacement, and force, in a clear and repeatable way for use in a STEM education context. To make sure we met this request, our team created a house of quality to establish our most important functional objectives and engineering requirements. These decisions were reached by having the team member rank each functional objective and specification and averaging the values to display in the final product. The functional objectives and engineering specifications were ranked based on their importance to their clients, being our group, Table 3, and Dr. Becknell. How we ranked each functional objective and engineering specification was in a house of quality. And I know this may seem like a lot to take in. I'm going to go over the most important parts. These being the functional objectives are what's, and the engineering specifications are how's. The functional objectives are what we believe to be the most important to the clients evaluating the P.U.L.S.E system, and the engineering specifications are how we will reach those objectives. The highest ranked functional objectives were recording 20 or greater measurements during each impact of the data stream. Having multiple measurements during impact allows the data to be more reliable as it minimizes, say, a spike in velocity in a one-off instance. And our second specification was showing clear, easy to understand data. If our data is messy and unorganized, it'll confuse viewers and potentially invalidate our design process. And our third requirement was minimizing variation across tests. This goes along with showing clear and easy to understand data. If our data isn't consistent, it raises a question to the effectiveness of our P.U.L.S.E system meeting the customer request. To complete these objectives, we decided on the top 5 most important engineering specifications, being sensor accuracy, sampling frequency, variance across trials, sensor range, and time to set up the system. Sensor accuracy: if the more accurate sensors will give clearer data. Sampling frequency: a high sampling frequency creates more measurements during impact. And having low variance across trials reinforces the validity of previous trial data. And having a sensor of a wide range, being able to graph acceleration, force, displacement, and velocity helps a viewer understand what data they are viewing instead of just one graph. And having a low time to set up the system allows for more measurements to be taken, like say during a day full of testing, and a low setup time allows the system to be used by novice and experienced users. And along with these what's and how's, our team weighed safety and measurement accuracy as the most critical design priorities. Our team's P.U.L.S.E system underwent multiple iterations before reaching a final acceptable product regarding constraints on time and money. We had 1 semester and a price cap of $40 to complete the system. Octavio will go over more of these details on his side of manufacturing the product. I'm now going to go over the objective tree, which has 5 different objectives, being accuracy, simplicity, clarity, resolution, and repeatability. For accuracy, it's split up into 4 different parts. We want to measure acceleration, velocity, displacement, and force accurately. And for simplicity, we want the P.U.L.S.E system to have a clean presentation and a quick and easy setup. For clarity, we want a high signal-to-noise ratio, which will reduce randomness from data signals. And for the 4th objective, being resolution, we want at least 20 or more measurements during an impact. This will help us understand better what is going on during each impact. And for the 5th objective is repeatability. We want the peak impact signals to match within 10%, and we want variation within the test to be within 5% of each other. I'm now going to go over the DAME decision matrix, which is what we use to decide on what our final design is going to be. We have 13 different criteria and 3 different weights for each criteria. The 3 different weights are numbered 1 through 3, 1 being that it doesn't meet the criteria, 2, it adequately meets the criteria, and 3, it exceeds greater than the criteria. We weighed each iteration against our datum, being simply taping a phone to the cart and streaming the data from Firefox. And the winner of the DAME decision matrix was the remote access iteration, which featured the 3D printed phone case mounted into the cart, and we later improved upon this iteration to feature the 2-stage impact to slow down impact over time. I hope I explained the process we went through to accurately decide on each functional objective and decide on a suitable final iteration. And now I'm going to hand over the reins to Octavio to give you the behind-the-scenes details on how we came up with our how we manufactured our final design iteration.
The final P.U.L.S.E system has 2 main components that work together. The first is the cart. We designed and 3D printed a custom PLA case in Fusion 360 by heading to GrabCAD, finding an iPhone 17 Pro Max case, scaling it down, and adding a box to the bottom of it to fit in the slot in the cart. It slots directly onto the provided cart and creates a snug, repeatable mount for the iPhone. The phone sits flush, and importantly, the phone doesn't shift between runs. That consistency was non-negotiable for our repeatability requirement. The second component is the deceleration enclosure. This is a Welch's fruit snacks box, found material as required, that we modified by removing the top and cutting an opening in the front so the cart can roll in freely. Inside, there's a floating piece of memory foam with cut channels. On impact, the cart drives that foam rearward into a second fixed piece glued to the back wall. We also added 2 additional foam pads on the exterior back of the box to cushion it against the wall. That gives us a 2-stage deceleration system. Here's the full bill of materials. The total out-of-pocket cost for the system was $21.65. The biggest line item is the memory foam mattress topper at $19.99 retail, but we only used a small portion, so the actual material cost was about $1.99. The PLA filament for 3D printing for the phone mount came to 40 cents. Tape and super glue brought us to the $21.65 total. We came in well under the $40 budget constraint, and the most expensive piece, the foam, does double duty as the core engineering element of our deceleration system. Now let's talk about how the final design actually performs against our engineering specifications. The top priority spec was recording at least 20 measurements during the impact window. We set an internal target of a 0.2 second impact duration. Running Firefox at 100 Hz, that gives us 20 data points exactly within the window. We hit that target. Now, our house of quality listed a sampling frequency target of greater than 1000 Hz. Firefox maxes out at 100 Hz. That's a gap. And Noah will get into the data analysis in detail, but I'll say this. Even at 100 Hz, we captured a clean, well-resolved impact curve with enough data points to extract peak acceleration, velocity, displacement, and force. On variance, our spec was less than 5% across repeated trials. Design choices we made, the rigid foam mount, the enclosed foam system, the guide wings, all work together to make each run as identical as possible. The data bears that out, and again, Noah will show you the numbers. Setup time was under 120 seconds. Place the box at the wall, set the cart on the ramp, open Firefox, hit record, one person, under 2 minutes, that's it. What you're watching now is the Fusion 360 assembly animation. Fusion model shows the phone mount geometry, how the case geometry locks the phone into a fixed, repeatable position within the cart body. Next, we have the full system in action. The cart rolling into the enclosure, the floating foam making contact and compressing rearward into the fixed back piece. You can see in this animation, the foam going inside the other foam represents the compression of the foam together. The cart doesn't just hit a wall, it progressively decelerates through a controlled deformation of the foam. That's what gives us the clean, gradual impact curve rather than a sharp spike. Now, we will be talking about our prototype iterations. Before I go on, I want to be upfront about something. We went through a lot of iterations on this project. Every time we tested, we found something that needed to change and improve. What I'm going to show you are the 3 most prominent ones, the ones that represent the biggest shifts in our thinking. Iteration 1, the straw rail system. Our earliest iteration used a straw rail system, but here's the key detail. The cart itself was not on the rails. The rails were there to guide 2 foam blocks. A sliding foam piece sat on the rails between the cart and a fixed foam block at the end. The idea was that the cart would roll in, hit the sliding foam, and that foam would travel along the rails and compress into the fixed foam behind it. A 2-stage energy transfer. On paper, that's actually a pretty elegant concept. Problem was the straw rails themselves. Under repeated impact loads, they would fracture and break at the point where the foam was transferring force. You can see that marked on the diagram drawing as the fractured point. And once a straw broke, it wouldn't stay in the same position for the next run. The rail geometry changed every time, which meant the foam path changed, which killed any chance of repeatability. We couldn't get consistent data from a system where the track was different each run. What we took from this iteration, though, was the 2-stage foam concept, a sliding piece compressing into a fixed piece. That idea survived. We just needed a better way to contain and guide it, which is what led to us to the enclosure. Iteration 2, foam cutout pattern change. Another key iteration was in how we cut the floating foam piece. Early on, we experimented with a more aggressive cutout pattern. You can see here a grid of rectangular holes, thinking that more material removal would increase compliance and lower peak acceleration. But testing showed us the opposite. The more we cut away, the less control we had over how the foam compressed. This deceleration became irregular. What we needed wasn't less foam, it was more predictable foam. So we moved to a simpler, cleaner slot pattern that compresses more evenly and produces a smoother, more reproducible deceleration curve. Iteration 3, final, full enclosure with wings and back foam. The final design added the full cardboard enclosure, guide wings on the cart to eliminate side-to-side drift, and the back and exterior foam pads to prevent the box from bouncing away from the wall on impact. Each of these changes was a direct response to something we observed in testing. The enclosure fixed repeatability, the wings fixed lateral drift, the back pads fixed box movement, and added more time for the impact. Every addition has a specific, measurable reason behind it. This is the P.U.L.S.E system in use. The cart loaded onto the ramp, released, rolling down and impacting the foam inside the enclosure. And here, slowed down, is the moment of impact. Watch the floating foam compress rearward. You can see the 2-stage system doing exactly what it was designed to do. The cart doesn't stop instantly, it decelerates progressively as the foam absorbs and transfers energy. That progressive deceleration is the whole engineering challenge here. Our job wasn't just to stop the cart, it was to stop it in a way that produces a clean, measurable, repeatable impact event. And I think the data Noah's about to show you confirms that we did exactly that. With that, I'll hand it over to Noah, who's going to walk you through exactly how we process the raw Firefox output in MATLAB and what the data tells us about P.U.L.S.E's performance.
Hey everyone, I'm Noah Arseneaux, and I'm going to be talking about the data side of the presentation. Here's the raw acceleration versus time graph you get over the entire time of the test. Before we even release it and after we release it is shown here, so you can see a bit of a shape of what's going on. To better see the shape, I have a smooth version of it using Savitsky-Goulet filter 11, 11 sample polynomial order 3, which preserves the high signal frequency components like the peak shape better than a moving average would. The figure shows the general shape of what's going on. You can see a release point, you see before and after anything happens. This graph minimizes a bit of that randomness and spikes you see from the previous graph. So you can see a general idea of what's going on here. To match the peaks, I set all impacts to a matching time axis. And you can see like they're very similar, right? They look super similar to each other. To quantify that repeatability, we have the fact that all of our peak accelerations are within 5% of the average peak acceleration. The average of the three values is negative 39.1 meters per second square. Test 1 is 3.9% away from that. Test 2 is 2.1% away from that. Test 3 is 1.8% away from that. All within 5%. It's a very repeatable test. Match the peaks again, right? You could see a zoomed in version of that. They're very close to each other. Test 2 and 3 are nearly identical. Test 1 a little farther, but well within 5%. Due to the sampling rate of 100 Hertz, which is one data point every 0.01 seconds, you could see that there is exactly 20 data points for test 1. There is 0.2 seconds between the start and the end of the impact. Do the math, 20 data points exactly. Test 2 has 21 data points because there's 0.21 seconds between the start and the end of the impact. Test 3, 20 data points because there's 0.2 seconds between the start and end of the impact. So we have 20 data points for each test, easily. To calculate velocity, I use the integrated trapezoidal integration method in MATLAB. And it's negative here because I just took the integral of the impact. Basically, right before the impact happens, the velocity is going to be 2.6 meters per second on average. And the displacement of our system from the impact is 0.25 meters. To calculate that, I use integrated trapezoidal integration method in MATLAB on velocity. Force was calculated using mass times acceleration. The accelerations I got were from the graphs and the data above. The mass of the cart was used for mass, which is 0.295 kilograms. Very similar graph to acceleration, and we knew this. To find noise from the sensor and other non-physical factors, I took the standard deviation of the baseline. The baseline I used was the values before anything's even happening to the cart, which should be 0 meters per second in theory. This deviated on average 0.593 meters per second squared. So for all the graphs and data shown above, this value is subtracted from all of them. To quantify the physical noise from the track, I got the root mean squared, standard deviation, and peak-to-peak noise metrics of the data of the downslope when the cart is rolling down the track. You can see all these values here. It's just to quantify it. To make data processing easy, the only thing you have to do for the code is change these A1, A4, and A5 values to velocity 1, velocity 4, velocity 5, displacement 4, displacement 5, displacement 1, or force. You can also change the graph title and axes in the code, but it's unneeded and unnecessary because you can just do that in a figure easily. You just double click on the title and you can change that. To conclude, we have that our accuracy requirement is met. We have all the data requested. It meets the simplicity requirement because you only have to change one element of the code to get everything different, right? To get your velocity, you just change one thing. To get displacement, one thing. It meets the clarity requirement by cutting off the values before and after the impact, subtracting the baseline standard deviation, and because the standard deviation is small in the first place, we don't need much to do for clarity. It meets the resolution requirement because there's 20 data points in each individual test, so we have all of that. And it meets the repeatability requirement because each peak is within 5% of the average. So thank you.
Hey bro, you started yet?
Yo.
And that's our project. Booyah!
Want more? Like what you see? Subscribe to our channel.